A little bit of UV vis spectroscopy, our last big spectra to look at. It's really easy to get lost in this one, so we're keeping it really simple. When we're looking at ultraviolet visible spectroscopy, what we're doing is we're scanning the ultraviolet and visible range, and we're looking for absorption. If there is absorption, we see this peak. So a little bit cleaner than IR in this respect, because we're just seeing this peak here. Okay, so in this particular case, what we're seeing is a peak appearing at 224 nanometers, and then we're seeing nothing else through that range. Okay, well, the important thing to know about ultraviolet and visible spectroscopy is that we are looking at pi bonds. So pi bonds are the only organic, or not only, but the primary organic functional group that has a gap that would allow for electronic transition in the ultraviolet and visible range. So that means what we're doing is exciting electrons from the ground state of our p orbitals to their excited state. Okay? That's what that matches. So if you change the energy of the pi system, you're going to change the energy, the lambda value, that you're going to see a spectrum peak appear. So this is where molecular orbital theory kind of comes in. Okay? And don't freak out and panic. But what we're looking at is taking electrons from that highest occupied molecular orbital. So if you remember, we went through and we tried to create molecular orbitals with sigma, pi, and all that fun stuff. But then what we would do is populate those orbitals with electrons according to the pi system. And what we're talking about is taking the electrons from the highest occupied molecular orbital, and when we hit it with ultraviolet light, those are going to jump to the lowest unoccupied molecular orbital. That transition happens to fall in the ultraviolet invisible range. We do have the potential to kick electrons from other places, but those other places tend to fall outside the ultraviolet invisible range, so we don't actually see them. Okay? So really what we're concerned about is that gap between the HOMO and the LUMO. The smaller that gap, the less energy we need, and the more into the visible range it can be, potentially even exceeding out of visible and going into IR. The larger that gap, the more purple or higher energy light needs to be used to cause that absorption. So what we're referencing for that absorption value is what is known as the lambda max. That's the maximum peak, okay, or where we get a big peak in our absorption. And wherever that appears, that's what we would identify. Okay, we can reference Beer-Lambert law and all of that, and we could use that to back calculate concentrations, all sorts of other fun stuff. But that's for another day if you really want to. The big thing that you need to be getting out of this is what happens to that gap as we change the pi system. So this slide does a really good job of showing that. So what we're talking about is we're starting with just a single pi bond, so one pi bond. Remember, the pi orbitals, or the p orbitals, are higher in energy than the sigma, so those are going to generate our HOMO. Okay? To jump up to the LUMO is going to require X amount of energy. Well, there's nothing really causing that gap to shrink. This is a single pi bond, so it's very high energy. So we expect a very large gap there. So that gap might actually come in as purple energy, so violet energy, so large energy. Well, what happens if we add a second pi bond? Okay, well, that second pi bond, as long as it has the ability to do resonance, right, which this one does, so a second pi bond that is conjugated, keyword being resonance, that drops the pi bond energy just a little bit. It's not the same as having two pi bonds. Okay, and so what ends up happening is we'll get a slightly lower first pi bond, and we'll get a slightly higher second pi bond. And why is that important? Well, the gap then between the HOMO and LUMO, if we look, has now shrunk a little bit. So we're now going to need lower energy to make that transition. So we could move from purple light to, say, orange light. I think I wanted green, but oh well. If we add yet another pi bond that allows for, again, conjugation, that conjugation now decreases the gap in between even further, which then means we need even lower energy. Okay, in this case, red light. So what I might ask would be, given two of these, which one would you expect to have higher or lower energy? Okay? Or how could we decrease the amount of energy used for an individual structure, and talk about trying to create that pi bond overlap, okay? Or that resonance option. So this is where resonance is really coming into play. Conjugation is really just another way of saying resonance. We can look at it through a big table, and yes, this gets daunting, but with all things that you analyze, what you want to do is break it down into the simplest comparisons first. So let's compare a couple of these. All right, let's start, whoops, that was not what I meant to do. Let's just start with those two, okay? So pi bond, but now we have a couple extra carbons. Okay, so we note the energy does change. We do see a shift in our wavelength. Okay, how big of a deal is that? So let's start to pull in some other information. So 2 pi bonds. Interesting, it increases again, but really not very much, particularly in comparison to the one or the hex 1-ene. We're not seeing a huge difference in energy here. Let's see, is the next one? No, I don't care about that one. Got to be artful in where we erase. No, come on, where's some conjugated ones? There's one. So now we're bringing in 2 pi bonds, right? Okay, what happens to the energy? Well, 2 pi bonds, we would expect somewhere in that 160 to 180 range. And if we look at the wavelength, oh my goodness, that jumped to 200. Why are we seeing such a large jump? Well, that large jump is because those pi bonds are conjugated with each other. That conjugation is changing this, allowing it to work out better. We could look at the cis, but that's going to be more complicated than I want to look at. If we add, no, it's like a game of memory, except my memory is awful. Let's jump out to triple bonds. We're going to do, no, come on, where's a triple bond? How about there? Ta-da, look at that, triple bond. 3 bonds, we might again expect a big jump. Whoa, that's a 60 unit jump. Okay, why is it making such large jumps? Well, it's again that conjugation. So when we start to bring in some other pieces, say here, just a cis double bond, well, yeah, we might expect more energy, but not a whole lot more. And if we look, there really isn't a huge difference. Okay, another one, trans, again, not a big difference. If we make it cyclic, okay, the cyclic doesn't really contribute a lot. Okay, the double with slightly more substitution, a little bit higher. So what we're trying to see is that we don't see these big jumps until we get conjugation. That conjugation is what's causing the big shift. Okay? Why does this become cool for us? Well, if we look at actually the vast majority of the ones that are being shown here, all of these are all wavelengths 340 and down. Okay? So those are all deep in the UV. We aren't going to see that. But this molecule starts to come out at 455. Why is that important for us? Well, 455 is in the visible range. That molecule absorbs blue light, and therefore we can't see the blue light. What does it not absorb? All the red-orange colors, which means that molecule gives us red-orange. That's beta-carotene. That's the color of oranges. Because those pi bonds are all conjugated, look at how much conjugation there is, we're getting an absorption of visible light. Now we can see it. So if you want to think about like dyes of shirts, okay, the colors of different materials that you see around, those are usually due to organic molecules. And it's the organic molecules and the conjugation of those pi bonds, that resonance ability, that actually gives us the colors that we see. That's kind of cool. Right? So we get kind of a neat effect that comes out of it. And really the big thing that you need to remember is that as we add more conjugation, that HOMO-LUMO gap shrinks, which is what's changing that energy, allowing us to actually see it. And with that, I believe we've got another sub 10-minute video, 10 seconds. Close enough.